Hello everyone. In this video I will go over various examples for review. So let's get started. Now let's look at this example. Here we want to calculate the Laplace transform of this expression and we have quadratic term and linear terms here. So it's not difficult because we have in our previous videos also we have talked about the Laplace transform, and you can use the linearity of the Laplace transform and take care of these one by one. And we can take out the constant terms out of the Laplace transform, and we know that the Laplace transform of t square is given by 2 factorial divided by s to the power 3. And similarly for the Laplace transform of t, we know now the rules of the transformation. This is given as 1 factorial divided by s squared. And then for the Laplace transform of 1, we have 1 over s, and then that is multiplied by 2. So you can just organize this and write down the final result as given here. The next example, we are trying to find the Laplace transform for this expression. This time we have a sine square here. For the exponential term, we know that the Laplace transform of this expression is actually given by 1 over s minus 2. So for this part, actually, we can directly write now this term and then take care of this sine square part. And for this one, we can use the trigonometric identity to simplify this expression. And basically, from trigonometry, we know that the cosine 6t can be written as 1 minus 2 times sine squared 3t. And you can write down sine squared 3t now as 1 minus cosine divided by 2. So you can, as you see, you can write this equation based on this trigonometric identity. And we already know what's the Laplace transform of a constant. This is 1 over 2 times s. And we also know what's the Laplace transform of cosine 60. That is given by this expression, basically s divided by s squared plus k squared. And here this corresponds to basically k in our previous notations, just to be consistent, that basically you take the square of this and that you get 36. And then finally, by combining both of these results, then we get the answer for this question. In this example, we want to calculate what's the inverse Laplace transform for this given expression here. And for these type of expressions, our general strategy is usually to simplify into more basic fractions or expressions. And here we can do that. We can actually rewrite this expression in terms of these three fractional forms as a over s, b over s squared, and c over s plus 2. So by looking to the denominator, we decompose this into three components. And then our goal is to solve this equality and find out what is this a, b, and c. We need to find out these. And this is just based on algebra, common denominator. You multiply with these terms. And then write down the left-hand side of this equation. This is the left side. And on the right-hand side, I have as squared, cs squared. So a plus c must be equal to the coefficient here, which is 1, right? This is 1 times s squared. So I can write down my first equation here. And then I have 2as plus bs. So in other words, these two terms, there is no s term here. So 2a plus b must equal to 0. And then for the b, we have 2 times b must match with the minus 1 here. So we get immediately b equals to minus 1 over 2. And once we solve for b, then we can obtain a equals to 1 over 4. And then it will follow as c equals to 3 over 4. So once you obtain these coefficients, now you can rewrite this expression in terms of a, which is 1 over 4 here, times the inverse Laplace transform of this fraction, which is 1 over s. And then we have b times inverse Laplace of 1 over s squared, and c equals to 3 over 4. So just write these coefficients one by one, and then take the inverse Laplace transform of these more simple expressions. And we know that the inverse Laplace transform of 1 over s is 1. For 1 over s squared, that is t. And for 1 over s plus 2, that is exponential minus 2t. And then just combining this, we get the final answer. Now, here is another example. This time we want to calculate the eigenvectors of this matrix A. So our matrix A is given here. And remember, the eigenvalue problem was given by this determinant here, where this I is the identity matrix and this lambda is the eigenvalues that we want to calculate. So eigenvalues must satisfy this equation. And we just apply this. We subtract this lambda because this is the identity. So it will bring these minus lambda on the diagonal elements. And we will take the determinant. And we know how to take the determinant for a 2 by 2 matrix. You multiply these terms, and then there's already a minus sign here. So this becomes plus 14 equals to 0. Now your job is to factorize this and find the roots of this problem. And we have a quadratic because this is 2 by 2. If we had a 3 by 3 matrix, then this will be a cubic polynomial here that we need to solve. So our quadratic equation, we just rearrange these terms. We get lambda square minus lambda minus 6. And you know how to factorize these type of quadratic expressions. You can also trial and error. I mean, you can, if you have any difficulty here, you can also use the discriminant method as well. But this is relatively simple to factorize. So we can directly write down lambda minus 3 and times lambda plus 2. That will basically give us the roots of the eigenvalue problem. And basically these are our eigenvalues given as minus 2 and 3. So now in order to find the eigenvectors, we have already found the eigenvalues first. Now in the next step we need to plug in these eigenvalues and then find the eigenvectors corresponding to each eigenvalue. So for the lambda equals to 3, we plug in into our matrix. So we have 2 and 7. And then when we multiply this with our x1 and x2, this is again 2 by 2, but in a 3 by 3 matrix, then you will have x1, x2, and x3, for example. And on the right hand side, we need to get the 0 vector. So if we write down this equation, we get 2x1 plus 7x2 equals to 0. And notice that both equations will give you this identical equation. So from the first and second equations, both of them gives us this result. x2 equals to minus 2x1 over 7. In other words, if we let x1 to be a constant c, then our second coordinate will be minus 2 over 7 times this constant. So that gives us the first eigenvalue. We write it as 1 and minus 2 over 7. Because this common constant we can actually take out. And for lambda equals to minus 2, we do the similar operations. We plug in this value into our eigenvector equation. And then this is also going to give us the right-hand side equal to 0. And from this first and second equations, we get x2 equals to minus x1. In other words, if we let x1 equals to a constant c, then x2 will be minus c. So we can represent this as 1 and minus 1. So these are the eigenvectors we get for the corresponding eigenvalues for the given matrix. Here we have another example. Now, what are the eigenvalues for this matrix given as A? And we know that for the eigenvalue problem, we should solve this equation, which is the determinant of A minus lambda times the identity matrix. And if you subtract this lambda, so we get 3 minus lambda, 0 minus lambda, and then take the determinant. So you have this quadratic equation. And similarly, like in some other examples, you can try to factorize this, or you can use the discriminant method to solve the quadratic equation. But again, this is relatively easy to factorize. We can observe that this is lambda minus 1 times lambda minus 2. So that yields us the eigenvalues as 2 and 1. In the next example, we want to solve the ordinary differential equation given here as the second derivative of y minus 4 times y equals to e to the power 2x. So for these type of non-homogeneous problems, first we will solve the homogeneous problem, and then in the second step we will solve the non-homogeneous part of the problem. So for the homogeneous part, you will assume that the right hand side is 0, and then we can apply the characteristic equation method. This will give us r squared minus 4 equals to 0. And we get r can be plus or minus 2. So we can write down the homogeneous solution immediately, given by this y of h. H stands for the homogeneous here. And we use the arbitrary constant c1 and c2, and this represents our homogeneous solution. Now for the non-homogeneous part, we can let y of s to be equal to c3 times x times e to the power 2x. We have this extra x because one of the roots is already exponential 2x. We have this overlap, so we need to multiply this with an x, and then just take the derivatives. We take the first derivative of this solution that we are trying to fit into our equation. So if we take the derivative, we get this term. We differentiate the x, which is just 1, and then the derivative of the exponential, we have 2 times c3x e to the power 2x. And then in the second step, we should also take the second derivative, and this is the expression. And finally, substitute these back into our equation and try to find out if our presumed solution that we are trying to fit into our equation, does it make sense? And we can find out if there is any inconsistencies, for example, in this solution we are proposing, then it will not satisfy the ODE. And if we can solve for C3, then that will be our non-homogeneous solution, or this y of s. So we plug in everything back into the equation. We subtract this minus 4 times y. So these two terms cancel each other. And then we are left with this part. And here we can write this down as 4 times c3 times the exponential equals to e to the power 2x. So this implies c3 equals to 1 over 4. And basically, if c3 equals to this constant, it will satisfy our ODE. And therefore, we get the non-homogeneous part of the solution. And by combining the two solutions together, we can write down the final answer for this problem as given here. In this example, we want to calculate what's the general solution of this second order ODE. given by this equation here. So for these type of problems, this is already homogeneous. So we can directly let the solution to be e to the power rx. So that gives us the characteristic equation. We get r squared plus 8 times r plus 25. So here we can easily identify that this looks like a perfect square, but if I split this into this 25, we can split this. This is the characteristic equation. So we can write this as a perfect square, r squared plus 8r plus 16, and then plus 9. So we decompose this 25 as 16 plus 9, and then this makes here a perfect square plus 9. And then you can actually put this 9 on the other side as minus 9. But basically, since this is a perfect square here, on the right hand side we can substitute the minus 1 with this I squared, the complex number I. And we know that this I squared equals to 1. So we can put a small note here. This I squared equals to minus 1. So r plus 4 equals to plus or minus 3 times the complex number I, and we can obtain our roots of the characteristic equation. And that gives us the solution. So notice that the real part here goes to the exponential, and then the complex coefficient here goes to our cosine and sine terms. So that gives us the solution for the ODE. In this example, we want to solve a fourth order ordinary differential equation, and we have the third derivative, the fourth derivative, and the first derivative. So directly we can write down the characteristic equation for this problem. Here is our characteristic equation as a fourth order polynomial. Now we need to find the roots of this characteristic equation. And you can immediately note that you can take out the common term r, and then that gives you r cubed plus 3r squared minus 4. And you can also easily, I think, notice that r equals to 1 satisfies the equation, the cubic equation here, because 1 plus 3 minus 4 is 0. So I can do the polynomial division, and we can divide this third order polynomial with this r minus 1, which is one of the roots. So we can reduce this expression into a quadratic expression. So this is the polynomial division. We just divide just like dividing a number. We put r squared and then subtract this. We get 4r squared minus 4. So we write this as plus 4r. So basically that will give us 4r minus 4. And finally, we obtain this quadratic expression. And this brings us here. We have already identified the r equals to 0 as one of the roots, and then r equals to 1 is the other root. Now we need to take care of the last term here, but this one is a perfect square. This is the square of r plus 2. Therefore, we can say we have the roots of the characteristic equation, but the last root r equals to minus 2, this is a repeated root because of the square here. So it is repeated twice. So for the repeated roots, we write down first the root, the coefficient itself as e to the power minus 2x, and then we repeat it one more time by multiplying with the powers of x. So if this was repeated 3 times, then we will have actually one more term with x squared times the exponential. So the first term here is to the power 0, that's just 1. So we have an arbitrary constant c1, and then we have e to the power x. And then for the third root, we have e to the power minus 2x. And then finally we have the x times e to the power minus 2x. So this combined all together gives us the general solution for this problem. In this example, we are asking what's the Wronskian determinant of the functions given by y1, y2, and y3. So the Wronskian determinant, we also use this to check if we have linearly independent functions. And basically the elements of the Wronskian determinant, first you need to write down the functions itself, y1, y2, and y3. And then you need to go for the derivatives. Write down the first derivative of each function. So these are the first derivatives of each function with respect to x. And then we need to go to the second derivatives, again applied to each of these functions. And if we do that, so these are the functions itself, y1, y2, and y3. And then we take the derivative of x, which is 1, take the derivative of x times ln x, that is ln x plus 1. The derivative of x squared is 2x. And then take the derivatives one more time, so you get 0, 1 over x, and 2. Now, we can take the determinant of this expression, and actually, if this determinant is not equal to 0, that means we have linearly independent functions. And here we can do one more step to simplify this determinant. We can multiply the second row by minus x and then add to the first row. So that will make this 0. And then we have minus x times ln x. That will actually eliminate this term. And then we have minus x. And then minus x times 2x, that is minus 2x squared. And then we have a plus x squared. That gives us minus x squared. And then you just write down the second row and third row. Now our determinant is simplified further. So we can use this basically element, because this column, we have two zeros already. So whatever we multiply with 0 is going to be 0 anyway. So the only non-zero term is here 1. So we have minus 1 because this is the index here is, this is the second row, first column. So minus 1 to the power 3. That gives us a minus 1 as a coefficient. And then we need to take the determinant of this submatrix for these terms. So this submatrix, the determinant is minus 2x plus x. So that gives us the final result equals to x. So this completes our examples related to the various topics in the ordinary differential equations that we have covered.